Hello everyone, welcome to the section 6.1 notes where we're going to introduce this idea, which is solving systems of linear equations. What we were doing in 5.1, but we're going to use matrices this time. Now we don't get very much into the ins and outs of how matrices work. That's for another class called linear algebra, but we're just going to see this one application for matrices where we can solve system of equations without keeping track of the x, y, and z. All that we need from this system to solve it are the coefficients. This number 5 in front of x, the -2, the -3, this 0 over here. As long as we have all the coefficients, we can solve this one. And that especially makes it a nice application for computers, because computers have a big problem with algebra and understanding how variables work. But what computers can do is they can crunch numbers. And so we're going to turn this into just a big block of numbers and see how we can carry on solving the system from there. So when you see this word, the augmented matrix, what an augmented matrix is it's on one part, it's what's called the coefficient matrix. And I'm going to just draw in here a few details, a little bit more details than what we're going to really get into, but just so we can see how this works. Coefficient matrix is going to have all these coefficients that are on the left side of the equations here. So we've got 5, -2, -3, 1, 1, and 0, and then 2, 0, and -3. These zeros are necessary as placeholders over here. We could even write 0y and 0z in the place of these missing variables in these equations. Then you can see that the coefficients are 0, and these coefficients are the ones that we also don't write, but we can understand it goes 1 times x, that makes x, so it should be a 1 there. Now if we write another matrix, which is a tall skinny one, this will be called a column vector. If you carry on into some other math classes, all this terminology will reappear because matrices are a big deal, but this column vector should just have the variables x, y, z. And then we go equals, and on this side we've got the other sides of the equation, 0, 5, and 4. Now we don't get to talk about how matrix multiplication works, but suffice it to say if we multiply this coefficient matrix times this column vector, we get this matrix on the other side, and this consolidates our whole system of linear equations into just one equation, but this time it's a matrix equation. Now what it means augmented matrix is we just chop out, I'm going to draw a little dotted line here, we chop it there, and we chop it here, and we chop out all this middle stuff, we get rid of it, and we just make a matrix that has those numbers. 5, -2, -3, we had this is where we cut it, and then we go 0 on the other side. Then we've got 1, 1, 0 with the 5, and 2, 0, -3 with the 4. And so it's called an augmented matrix. Augmenting is like making something bigger or adding to something. And so we took the coefficient matrix and augmented it by splicing onto the side this matrix that has the things on the other side of this equal signs. And so this is an augmented matrix for the system, and that's what the problem was asking for. So we're done right here. That's going to be the easy part, is finding an augmented matrix to correspond to a particular system. Now let's see it in action. Something that we can do with this augmented matrix, because here we have an augmented matrix. Sometimes I just draw the dotted line instead of this vertical bar, but it's the same thing, and we can understand that this is representing a system 2x minus 6y plus 4z equals 10. We should know that this column right here is all of the x coefficients, these are the y's, and these are the z's. They do need to stay in that same order. And so we're not at liberty to move these columns around, because then we're changing which coefficient corresponds to which variable. But keeping in mind what we're allowed to do when solving a system by either substitution, this should go z, solving an equation by substitution, or even just having one equation and doing some algebra to it, there are certain things that we're allowed to do. For example, we're allowed to add the same thing to both sides of an equation. We're allowed to multiply an equation by something on both sides, as long as it's the same thing. And then this is something we don't know when we're dealing with just one equation, but it would be perfectly fine with this system over here, which this system comes from that matrix. It's no problem at all just to switch two of these equations switch which order we write them. We could write this equation first, write this equation under it. That doesn't change up the system. And that's going to be the most basic kind of what we're calling elementary row operations. This thing, row operations, sometimes you call elementary row operations, or just row ops for short, elementary row operations. There are only 3 of them, and one of them is just to switch the rows. That's very basic. It's like writing the equations in different orders. Something else that we can do is multiply a row by a number, and that corresponds to multiplying an equation on both sides by the same number. Now that's something we would do in elimination all the time to be able to subtract the equations and get something to cancel, is that sometimes we need to multiply a whole equation by a number, and it's perfectly legal to do it. That's why here we're able to do this row operation, which is telling us to multiply row 1 by 1/2. And I think a better way to write this one would be to put a little arrow here and say that's going to become the new row 1. So this arrow is saying what to replace. We're taking half of row 1 and replacing row 1 by that. So we would go just all these numbers times a half. So it'd go 1, -3, 2, and 5. Instead of 2, -6, 4, and 10, we're just dividing them all by 2. That gives us a new row 1. The other rows wouldn't change. And the result of doing an elementary row operation is to get a new augmented matrix that just has some of the rows changed. In this case, we only changed one of the rows. We changed row 1 by multiplying it times a half. So this is what we get. That's the new matrix when we do that row operation. Now the third row operation that we're allowed to do is to add rows together, which that's the critical step in elimination. When I say add rows, it also means subtract rows, because we can add and subtract multiples of rows, and if you multiply a row times -1 and then add them, that's kind of the same thing as subtracting. So here, especially keep it in mind, we can do all of these operations. We can even do them multiple operations at the same time. We can multiply rows times numbers and then add them, or we can subtract multiples of rows from each other, do all kinds of stuff like this. But these are actually the only 3 operations that we're really allowed to do. If you think of something else that you would want to do, you should consider, can you do that when they're in the equation form? Here just moving the columns is dangerous, because if we switch this y column with the x column and then you turn it back into an augmented matrix, now you're going to think that those y coefficients are x coefficients, and it really messes it up. So switching columns is not a thing. There's nothing else. Those are the elementary row operations. And so here we've got a compound operation. We're wanting to take -3 times of row 1 and add row 2. And then let's see, I feel like this should become the new row 2. That's what we would want to do. And so I'm going to add on to this operation and say, take this quantity and make that become the new row 2. Otherwise it's not clear, should that be the new row 1? Should it be the new row 3? So this one will make it be the new row 2. So what does it look like, -3 row 1? That's going to be a row like this. It should be all of these numbers times 3. So 3 times row 1. It's going to go, the 3 will distribute to everything, and it's going to go 3 with -9, with 6, with 0. It's on the other side of the augmentation. And then we've got row 2, which row 2 goes just 3, 1, -1, and 7. That's our row 2 right there. And then we want to add these. So I'm going to go add. Let's see what happens. We should just add by the corresponding locations in here, the corresponding entries. And so 3 plus 3 goes 6. -9 plus 1 goes -8. 6 minus 1, because it's plus -1, so that's 5. 0 plus 7 goes 7. And so this is what we get when we take -3 row 1s, add row 2 to it. And this is going to be, oh wait, but it's -3 times of row 1. So I guess these actually I should change the signs. That was a mistake of not multiplying times -3. So let's come back here. The row 2 is all right, but -3 times of row 1. This should be a negative right here, -3. And it's going to go -3 times 1 makes -3. This would be +9. This would be -6. Now when we add them, this should be a little bit better because negative 3 plus 3 makes 0. That was the idea, was that we wanted a 0 right there. That's how I could tell to make it be a row 2. 9 plus 1 is 10. 6 minus 1 is 5. 0 plus 7, that's still 7. And so this is the new row 2. Now the new matrix that we're going to have, row 1 stays the same. Multiplying row 1 times negative 3, we were just doing that for the purpose of this row operation, but that doesn't mean we permanently change row 1 like that. Unless we make an operation where we say, do something over here and make that be the new row 1. That changes row 1. This one, all that we did was change row 2 over here. And so row 2 is going to become 0, 10, 5, 7. Row 3 was 2, negative 2, 1, and 3. That's the augment. And that's the 1. And so that's the new matrix when we did this row operation. Now this kind of problem, we're going to have several operations that we need to do, but I'm going to try to explain the idea. Whenever you see, I'm going to scroll up a little bit, when you see this terminology, use Gaussian elimination, that includes this idea of doing it with matrices, but this one, it's trying to obtain a certain form for the matrix, and that form is called the row echelon form. And the way row echelon form looks, I'm going to put in this word which is called reduced, because you can see Gaussian elimination, sometimes called Gauss-Jordan elimination, and they are slightly different. Gauss-Jordan elimination is where we're looking for the reduced row echelon form. Gaussian elimination, we just want row echelon form, which is where we get 1s on this main diagonal. We should have 0s below the main diagonal. And then we don't know what's going to be on this side. If you just have a mysterious entry in a matrix, you usually put an asterisk there. Row echelon form, it also does not prescribe what should be above the main diagonal. So we're looking for a form like this. We want to get the 1s on the main diagonal and then 0s below. And what that's going to allow us to do is that this last equation would read z equals whatever's there. And then you can take that one and plug that into this equation above, because this equation above is going y plus some kinds of z equals some number. Of course, these asterisks are all different. These might not be the same number here. And if once we know z is equal to this number, then you just plug it in. This equation now will only has y as a variable, so we can solve for y. And then we'll have y and z. We plug them into this one, and we'll find x. And so that's all fine and dandy. The reduced row echelon form is where we take the little bit of extra time to get also 0s above the main diagonal. And you can see how this would be a nice form to have, because then these equations just go x equals whatever's there, y equals whatever's there, and then this is 0x plus 0y plus z, so that's z equals some number. And there the solution's just read as this ordered triple right there. And so I'll probably go for a reduced row echelon form on this one, but it doesn't really matter. What this says is use matrices to solve this one. So I'm going to start out with an augmented matrix, 1, 1, negative 1, and negative 2. Then 2, negative 1, 1, and 5. Negative 1, 2, 2, and 1. So that is our augmented matrix. Now, in order to get a 1 on the main diagonal, we should start here, starting in the first column. This already has a 1, so we're actually done with that part. And then what we should try to do is get 0s below. So we want this 2 to become a 0, we want this negative 1 to be a 0. And we should always get it by adding or subtracting multiples of this row where we just got the 1. Because you can see if we take row 2 and we subtract 2 copies of row 1, then it's going to go 2 minus 2. 2 copies of row 1 will have a 2 right here. 2 minus 2 makes a 0. That's the 0 that we want. So this should become our new row 2. Similarly, we can get row 3 to have a 0 right here if we just add these rows. So if we just go row 3, we add a row 1, that can be the new row 3. That's going to have a 0 right here. So let's see what's going to happen. These don't change row 1, so I'm going to write down row 1 again. And then row 2, we're subtracting 2 times of this, so 2 minus 2 makes 0. -1 minus 2 makes -3. 1 minus 2 times of this, that's like 1 plus 2 makes 3. 5 minus 2 times of this makes 9, because that one was going 5 minus 2 times of -2. That's 5, or that's row 2 minus 2 times of row 1. Looks like this, that goes 9. That's how I got that 9. And then row 3, we're just adding them. So 1 plus -1 is 0. 1 plus 2 makes 3. -1 plus 2 makes 1. And then -2 plus 1 makes -1. So we're here. Now the next thing to do would be to get a 1 on the main diagonal, just going one column over. We want to get a 1 right here. And the easiest way to get a 1 someplace is just to divide that row by whichever number is here, or else multiply by times the reciprocal. So if we just multiply this row times -1/3, that's going to do it, or else you can think of it as dividing by -3. But row 1, we don't want to change for now. I'm just going to write down row 1. Row 2, we're going to change like that. We're going to make -1/3 of row 2. That can be the new row 2. And row 3, we also won't change it. And so row 3 is going to be the same. I'm going to write that down. Row 2 is going to change by dividing these by -3. So it's going to go 0. -3 divided by 3 is 1. That's exactly what we wanted. And then 3 divided by -3 is -1. And finally, 9 divided by -3 is -3. So we're right in here with it. We're getting closer. At least now we all have 1s on the main diagonal. It's just that the main diagonal is about to get messed up when we get rid of this 3 right here, because we need to get 0s above and below the main diagonal in this column. Here we can subtract. We can go row 1 minus row 2. That can be the new row 1. So that's going to go 1 minus 1 makes 0, and it doesn't mess up this row before because it's going to go 1 minus 0. We'll still have a 1 there. So this will give us a new row 1, and if we go row 3 minus 3 copies of row 2, that can be our new row 3, and then it's going to go 3 minus 3 to make 0 right over here. So that's going to work out. So what will we have with this one? It's going to go 1 minus 0, and I'm thinking, by the way, just doing component-wise, row 1 minus row 2. So 1 minus 0 is 1. 1 minus 1 is 0. -1 minus -1 is also 0. And then -2 minus -3 is 1. So that's a nice looking row 1. And then what about row 2 is going to stay the same. We didn't change it. And row 3, we are changing it by subtracting 2 times of row 2. And I meant to say 3 times if I didn't say 3 times of row 2. So it's going to 0 minus 0 is 0. 3 minus 3 is 0. 1 minus 3 times of -1. 3 times of -1 is -3. If we subtract 3 of those, it's like adding 3, so this makes 4. -1, I'm going to write this down. -1 minus 3 times of -3. That's going to be this last entry. That goes plus 9, so this makes 8. And then we're getting super close. These first 2 columns are locked in. They've got reduced row echelon going for them. And that last move was convenient because it gave us a 0 right here, which we wanted to have anyways. But what we need on this next operation is to make a 0, right? Not a 0, a 1 where this 4 is, because we're getting 1s on the main diagonal. So we need to go 1/4 of row 3 to be our new row 3. And so we're going to have 1, 0, 0, 1, 0, 1, -1, -3, 0, 0, 4 divided by 4 is 1, 8 divided by 4 is 2. And we are just right in there. I'm going to come down. Let's see. The only thing we have left to do is to get a 0 right here, where this -1 is, because we've got our main diagonal all set. Now we just need 0s above here. And so what I want to do, can you tell how we should get a 0 right here? This one goes 1 in that spot. So what if we simply go row 2 plus row 3? That can be our new row 2. Row 1 and row 3 can stay the same, so they're going to be 1, 0, 0, 1, 0, 1. Oh wait, this one is going to change. It's not -1 anymore. And so I was charging ahead, but what happens with this? We're adding row 2 plus row 3. So row 2 plus row 3, that goes 0 plus 0, that was this 0. Here 1 plus 0 makes this 1. -1 plus 1, that makes 0 right here. -3 plus 2 is -1. And then row 3 didn't change at all. So this is our reduced row echelon form for this augmented matrix. And can't you see from this one, the first row goes x equals 1, the second row goes y equals -1, and the third row goes z equals 2. So this, we can write the solution like this, or we can write it as an ordered triple 1, -1, 2. And that's it. That does it for that one. Now, this problem, solved by Gauss-Jordan elimination, we could carry on the same way, but I want to just look at doing this on the calculator. It's so convenient. Alright, now the calculator has this matrix button, if you ever saw it. It's these blue letters. So if you go into that menu, second x reciprocal gets us into matrix. And this matrix menu, you can call the matrices right over here. Like if I just go enter, and enter again, it's going to tell me, oh, it's undefined, because I've never made a matrix A. But if you go back into matrices and you go to edit, this is where you can define them. So see, A doesn't exist, or else it would have dimensions next to it. If you just go enter, it's just an empty matrix right now. We need to put the augmented matrix for the system in there, so why don't we first do that? That's a little thing to do. Unless you can just tell by looking at it. I can kind of just tell on this one. The dimensions are nice though to understand. Dimensions always go row times columns. Well, not times, but by. Like row by column. It's this many rows by this many columns. It has, this particular matrix has 3 rows and 1, 2, 3, 4 columns. So that makes it columns. That makes it a 3 by 4 matrix. 3 by 4 is the dimensions. And so we're trying to make over here a 3 by 4 matrix. We have to input the dimensions. And once you make it 3 by 4, now it has the right number of entries. Okay, so these coefficients, I'm going to go back and get rid of these marks so we can see the coefficients. Coefficients go 1. So it's 1x, 1y, -1 z's. And I want to make sure that's the right kind of negative sign. There, that'll work. You can't go -1 with this minus, it has to be the negative. And then -2 is that number, so then we've got 2, -1, 1, and 5. 2 minus 1, 1z equals 5. And then we have -x, that's -1. We've got 2 y's, 2 z's, and then it goes equals 1. So this should be our augmented matrix. Now I'm going to quit out of this because I don't want to keep changing this matrix at all. I'm done defining matrix A, so I'm going to go second mode to quit. Come back to this screen. Now I want to refer to that matrix A that we just made, and I want to plug it into a function. If you go back into the matrices, so I go second x to the -1, that brings up matrices. Now you can tell I've made matrix A because it calls it a 3 by 4. But I want to come over here to math. This has some nice functions, and I'm going to scroll down, 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 down. I want the reduced row echelon form of this matrix, and that's what this means, RREF, reduced row echelon form. So I want to pick it. I'm going to select, or in this case, enter. And then I want to plug matrix A into this function. This is a function that takes matrices instead of numbers. And so the way I plug in matrix A is I go back to matrices, and there's matrix A, and I just go enter that matrix. Reduce row echelon form of matrix A, and then equals, boom. Reduce row echelon form of matrix A goes 1's on the main diagonal, 0's off the main diagonal, 1, -1, 2. And so that's going to also give us 1, negative 1, 2. We got this reduced row echelon form. We could have obtained it by some number of steps of elementary row operations, but the main thing here to know is you need to know how to do individual elementary row operations, how to go through this whole procedure and manually find reduced row echelon form by doing the elementary row operations. It's not as necessary, and I know it can be very time consuming, and so that's why I wanted to show how to do it on the calculator. We just get this one and we solved the system. It goes x is 1, y is negative 1, z is 2. And so that's the solution right there. And that does it for the 6.1 notes. I hope this was helpful to you, and I'll catch you in the next one. Thanks.